Yeah. Hello all. In my last lecture, I discussed construction of the MOSFET and also working. Okay. Means in working actually I discussed one case, that is VGS is varying and VDS is constant, right? Now in this lecture, now I will start with, I'm going to start with actually case 2. What is case 2 here? Case 2 is VGS is constant. Here we make the VGS is constant, VGS is greater than threshold, like that. Yeah, this should be constant. Why you have to put like this condition here? See, if you make this VGS is less than V threshold, what happens? Channel is not completely formed. That's why. So you can make like this. VGS is greater than or equal to V threshold should be constant, and which one is varying here? VDS is varying. Now in this case, VDS is varying. Okay. See here. First listen. Here we are making VGS should be constant and VDS is varying, right? So here this VDS equal to 0, for example. When VDS equal to 0, what about the current IDS here? Current IDS also 0, because there is no movement of the charge carrier from source to drain. Okay, I already told, I think in my in my previous lecture, okay, what is the use of the VDS? To enable the movement of the charge carrier, right? Okay, see here, even though the channel is created, if you are not given the VDS, there is no current or there is no electricity in the channel actually. Why? Here VDS should be 0. That's why. Okay. So when VDS is 0, then current IDS is 0, because there is no movement of the charge carrier from source to drain. Next, when VDS is increases by a small amount, when VDS is increases by a small amount, then what about the current IDS? The current IDS is linearly increases with VDS. Why it is linearly increases with VDS? Because okay, the MOSFET acts as a fixed value of resistor. Means the channel will act as a resistor. Okay, actually resistor is a linear element. What is the relation between current and linear actually, right? So right, current is linearly varies with voltage. Okay, yeah, write down these 2 points first. Yeah, first put the case 2. Put the case 2. Yeah, write down like this. VGS greater than or equal to V threshold should be constant and VDS is varying. Right? Yeah, write down. When VDS is 0, then current IDS is 0. Current IDS is 0. Because there is no movement of charge carrier between source and drain. Yeah, next point. When VDS is increases by a small amount, then the current IDS linearly increases with VDS. Because MOSFET acts as a fixed value of resistor. Right? Yeah. Copy this diagram. Yeah, copied now? Yeah, next one. See, when VDS is increases further, then this increasing VDS appear in the channel. This increasing VDS appear in the channel. You know that voltage is called as channel voltage. Which voltage? Channel voltage. Yeah, that channel voltage is maximum at the drain end, maximum at the drain end, okay, and minimum at the source end. Maximum at the drain end and minimum at the source end, because here the source is connected to ground and this one is connected to battery, right, or supply. Okay, that means here this is maximum and this is minimum. And also this channel voltage is used actually to make the channel junction as reverse bias, to make the channel junction as reverse bias, due to which the depletion region is increases. Okay, due to which the depletion region is increases, okay, at the channel junction. At the channel junction, you know that increasing depletion region is maximum at the drain end, minimum at the source end. Okay, so here how it is look like. See, all of you. See, this is our channel. Now I am representing channel with simply electrons because it is N channel, na? Right. Now I think this part is a depletion region. See here, depletion region is maximum. This is depletion region. Just it contain only acceptors. It contain only acceptors. Okay. It is maximum at the drain end and minimum at the source end. Okay. See here, depletion region is maximum at the drain end, means I think channel is minimum at the source end. Sorry, channel is minimum at the drain end. Sorry, here the channel is minimum at the drain end and maximum at the source end. As a result, the channel is in wedge shape or tapered shape. Wedge shape or tapered shape. Due to the wedge shape of channel, okay, the channel resistance is increases. Okay, channel resistance increases means what about the current IDS? You know, the current IDS is sublinearly increases with a slow rate. Current IDS is sublinearly increases with a slow rate. Okay, yeah, right out. Right at a point. When VDS is increases further, then the increasing VDS is appear in the channel. This voltage is called as channel voltage. Channel voltage. Yeah, underline channel voltage. Next point. This channel voltage is maximum at drain end, and minimum at source end. Next point. This channel voltage is used. To make the channel junction as reverse bias. Due to which depletion region is increases. At the channel junction. Yeah. This increasing depletion region is maximum at a drain end. Yeah. In bracket, channel is minimum. Yeah. Bracket close. Minimum at the source end. In bracket, channel is maximum. Yeah. As a result, the channel is in wedge shape or tapered shape. Right. Yeah. Due to wedge shape of channel, channel resistance is increases, channel resistance is increases, and current IDS is increases sublinearly. Current IDS is increases sublinearly. Yeah, underline current IDS increases sublinearly. Yeah. Yeah, copy this figure. Yeah, copied na? Yeah. Here most of the people are doubting, right? See here, channel resistance increases means generally current what decreases, right? But here I am saying current IDS is increases sublinearly. Yeah. Here what happened? See, before sublinear, I think the current is linearly increases. Means the growth rate is very fast. Okay. So here after some point means after some voltage actually here the current growth rate, the net rate will start decreasing. See, net rate start decreasing. Rate will decrease, but current increase. Okay, current increases. So here that rate will be sublinearly increases actually. Getting or not? So here why the rate net rate here decreasing actually here because of increasing of channel resistance. Okay, don't confuse. Here most of the people are thinking like the channel resistance increases means current should be decreased. Yeah, here the current should be decreases means which one is decreases? Growth rate. That rate will be decreased. See, here I think this region it is increasing very fastly, but here it is increases very slowly. Yeah, right. This slow increasing of current because of increasing of channel resistance. Okay, don't confuse. Next, the next one actually. See here, when VDS is made to very high. The third point actually, when VDS is made to very high. See, when VDS is made to very high, what happened? You know what happened? So here, the channel at the drain end, the channel at the drain end is almost zero. Okay, if the channel at the drain end is almost zero, means we can say the channel is said to be pinched off. Okay, here the channel is said to be pinched off at drain end, but see the source end actually, other end actually, the channel is maximum, due to which the few electrons are gets attracted due to drain end due to the high value of VDS. Okay, you know this increasing the VDS can attract the electrons from the source end, even though the channel is pinched off at the drain end, due to which okay the current IDS is constant. Current IDS is constant actually. Okay, write down. When VDS is made to very high, when VDS is made to very high, then the channel at the drain end is almost zero. The channel at the drain end is almost zero. That is, it is said to be pinched off. That is, it is said to be pinched off. But the channel at the source end is maximum. The channel at the source end is maximum. 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 Due to which few electrons are gets attracted. The few electrons are gets attracted towards drain end, and produce a constant IDS. And produce a constant IDS. Produce a constant IDS. Yeah, underline constant IDS. Next heading. Next heading. Output characteristics. Output characteristics. Output characteristics. Yeah. Yeah. Listen. See, output characteristics are drawn between IDS versus VDS by keeping which one is constant here? VGS is constant. Yeah. Here VGS is constant. I think it is greater than or equal to threshold voltage, right? Don't forget that one. See here, when VDS is 0, what about the current IDS? 0, because there is no movement between source and drive. Current IDS is 0. Now, when VDS is increases by a small amount, then what about the current IDS here? You know, the current IDS is, I think I told, na, linearly increases. See, linearly increases. Linearly increases. See, when the VGS is increases further, what about the current IDS? You know, the current IDS is sublinearly increased. Sublinearly increased. Actually, this part is sublinear. Sublinearly increased. Means the growth rate will be very slow because of increasing of channel resistance. When VDS is made to very high, then what about the current IDS here? The current IDS is constant, right? Current IDS is constant. See, this is the output characteristics of MOSFET. I think these characteristics are similar to BJT output characteristics, right? There we are controlling current, here we are controlling with VGS, means voltage. Yeah, copy. Yeah, next, see, based on the output characteristics, okay, my MOSFET is operated in two regions actually. One is linear region, another one is saturation region actually. Yeah, I think this part will be linear region and this what will be saturation region. Saturation region actually. Okay, you know, this linear region also called as triode region or non-saturated region. Means we can also say this is also triode region or non-saturated region. This is the saturated region, saturation region actually, right? Yeah, next one coming to linear region. What is linear region actually? Linear region is nothing but the region in which the current IDS is linearly increases with the VDS. That region is called as linear region. What is linear region? The current IDS is linearly increases with VDS, is called as linear region. Okay, you know, in case of linear region, my MOSFET acts as a fixed value of resistor. My MOSFET acts as a fixed value of resistor because it obeys Ohm's law. That's why it is also called as ohmic region. It is also called as ohmic region, non-saturation region, and also what? Triode region. Okay. And next one, when the MOSFET is in linear region actually. So when it is in linear region, see, whenever the VDS should be less than VGS minus VTH. Whenever VDS is less than VGS minus VTH, then we can say MOSFET is in linear region. Okay. Yeah, this condition for what? N channel MOSFET. Yeah, for P channel, what is the condition? For P channel, the VSD is less than VSG plus VTH. Okay, or we can also have one more condition, that is mod VDS is less than mod VGS minus mod VTH. Okay, then also MOSFET is a linear region. This is for P channel. Very important conditions. You can use this condition or this condition to check the region of MOSFET. Okay, both are valid. Yeah, write down here. Based on output characteristics, based on output characteristics, MOSFET is operated in two regions. MOSFET is operated in two regions. The first one is linear region. The first one is linear region or triode region, or non-saturation region, non-saturation region, non-saturation region. Yeah. Next point, the region in which the current IDS is linearly increases with VDS. Linearly increases with VDS. Yeah. Next point, in this region, MOSFET acts as a fixed value of resistor, because it obeys Ohm's law. So that it is also called as ohmic region. Yeah, underline ohmic region. Yeah. Next point, MOSFET is in linear region when, yeah, copy these two conditions. This is for N channel, this is for P channel. Copy na? Yeah. Next, saturation region. Yeah, suno yaar, saturation region means, saturation region is nothing but the region in which the current IDS is constant or maximum. Current IDS is constant or maximum. Yeah, that region is called as saturation region. You know, in case of saturation region, the MOSFET acts as a constant current source. With respect to what? VGS. Means if VGS changes, what about the current here? Changing, right? Okay, that's why it can act as a constant current source with respect to VGS. Therefore, we can also say the MOSFET is called as voltage control current source. Okay. And one more, in case of saturation region, my MOSFET acts as an amplifier. Okay. Next, when the MOSFET is in saturation actually, see, whenever, in case of N channel, whenever VDS is greater than or equal to VGS minus VTH, okay, MOSFET is in saturation region. Okay, next for P channel, the condition is VSD is greater than or equal to VSG plus VTH, and one more condition is there, that is mod VDS is greater than or equal to mod VGS minus VTH. Yeah, write down please. The region in which saturation, current IDS is constant or maximum. Right? Next one, in saturation region, MOSFET acts as a constant current source with respect to VGS. with respect to VGS. Therefore, it is called as voltage control current source. Voltage control current source. Yeah, underline voltage control current source. Yeah. Next, in saturation region, MOSFET acts as a amplifier. MOSFET acts as a amplifier. Yeah. Next point. MOSFET is in saturation region. MOSFET is in saturation region when, yeah, copy these conditions. Very, very useful conditions, because if you want to solve any MOS problem, okay, first you have to know the region of MOS. So here, to know the region of MOS, these conditions are very helpful, right? Yeah, put the heading IV relationship. In a MOSFET. Yeah. Here we are deriving for N channel. IV relationship in a MOSFET. Yeah. So here, before deriving IV relationship in a MOSFET, yeah, first listen. First here, listen here. Here, the gate and the channel is separated by oxide layer, right? Okay, this structure exactly resembles a parallel plate capacitor. Actually. So, what is the equivalent capacitance? Actually, the equivalent capacitance is nothing but COX is equal to epsilon OX into A by TOX. Epsilon OX A by TOX. Right? Yeah, what is this A actually? This A is nothing but area. So here, how we can represent the area of the channel is here. Here, this is length. This is the length actually. This is the total length. This is the width of the channel actually. Then area is nothing but L into W. Okay. Then what is epsilon OX actually? Epsilon OX is nothing but permittivity of the oxide, and TOX is nothing but thickness of the oxide, and COX is nothing but oxide capacitance. Or sometimes we can also define like this. This is nothing but COX is nothing but gate capacitance, right? Gate capacitance. Or oxide capacitance or gate capacitance are both are same. Okay. Yeah. Write down first this point. Write down this point first. Write down. In a MOSFET, metal means gate and channel separated by a oxide this structure resembles parallel plate capacitor its capacitance is known as oxide capacitance in bracket COX. Yeah, write down that one. COX is equal to epsilon OX into A by TOX. Epsilon OX into A by TOX, where A equal to area of the channel, that is L into W. L is the length of the channel, W is the width of the channel. Width of the channel. Next, TOX is the thickness of oxide layer. Thickness of oxide layer. Next, epsilon OX is the permittivity of oxide. Permittivity of the oxide. Yeah. Copy na? Yeah. Please copy this structure first. Copy this diagram first. Then only we'll understand IV relationship in a MOSFET. First copy it. What we want here, IV relationship in a MOSFET, right? See, in order to obtain the IV relationship in a MOSFET, here we make two observations. Here we can make two observations. The first one is when VDS is 0 here, we are applying some VGS. That should be VGS is greater than V threshold. That should be VGS is greater than V threshold. I think, see the channel actually, I think the channel is like this. The channel is like this, right? Now in this case, what is the charge density? What we did actually here? So here, when VDS is 0, the first observation is when VDS is 0, okay, we are making VGS is greater than V threshold, that should be constant. Then actually, tell me here, what is the channel in the, what is the charge in the inversion region actually? See, the total charge in the inversion region is nothing but how much? That is simply COX into W VGS minus VTH. What it is? QD equal to COX into W VGS minus VTH. When it is, so whenever the VDS should be 0. Okay, write on this point first. Write on the point first. See, to obtain the IV relationship in a MOSFET, we make two observations. First, VDS is 0. VDS is 0. Next point, write down. See, when VDS is 0, the charge density in the inversion region is given by the charge density in the inversion region. See, this is also called as inversion region. I already told, right? Is given by, write down, QD equal to COX into W VGS minus VTH. VGS minus VTH. Right. Yeah, consider this one as equation 1. Yeah. Now case 2, second observation actually. Now the second observation. See, when VDS is greater than 0. I think the channel is in wedge shape, right? I think that concept already we discussed. When VDS is increases, actually, I think it's going to be look like wedge shape, right? So when VDS is greater than 0, okay, then what happen actually? You know, when VDS is greater than 0, then the channel voltage is varies, means the channel potential is varies with respect to distance. In this case, what is the charge density in the inversion region? What is the charge density in the inversion region? In this case, actually QD equal to COX into W VGS minus V of X minus VTH. Okay, where what is this Vx actually here? Vx is nothing but channel potential with respect to distance at a point of X. Okay, right off. Second observation, right off. When VDS is greater than 0, VDS is greater than 0, the charge density the charge density in a inversion region is given by, QD equal to COX into W, VGS minus V of X minus of VTH. Yeah, I think do you observe or not the difference between equation 1 and equation 2? So in this case, I think the VDS is 0. In this case, VDS is varying, right? So this is V of X is nothing but I think VDS, right? Yeah, copy now. Yeah. Now tell me, what is the current in this channel actually? The current in the channel is nothing but what? It's simply QD into V, where V is the velocity of the charge carrier, right? QD into V actually. Okay, I think you know what is QD here. QD is nothing but COX into W into VGS minus VTH minus V of X into velocity, right? But what is velocity in terms of applied electric field? In our chapter 1, starting chapter, what is relation here? This velocity is nothing but mu into E. The relation between electric field and velocity is nothing but mu into E. Okay. Now what it is, I equal to, okay, here COX into W into VGS minus VTH minus V of X. What it is actually here, I think mu velocity is nothing but minus mu into E. Now this minus indicates the polarity of the charge carrier. Here our charge carrier is electron, right? Minus mu into E. Okay. Now what is I here? I is nothing but COX into W VGS minus VTH minus V of X mu into what is electric field in terms of voltage here? That is dV by dx. Electric field is nothing but voltage per unit distance, right? So that is dV by dx. Okay. Next, just rearrange this equation. I into dx minus COX into W. Okay. VGS minus VTH V of X mu into dV. Mu into dV, right? Now you can integrate this equation, okay, with boundary conditions. Here the channel is varying from what actually 0 to L, right? And here the voltage is vary from what actually 0 to VDS. 0 to VDS. Now here I am integrating. So integral 0 to L I into dx minus COX into W VGS minus VTH minus Vx into dV into mu. Okay. Now I think this will be integral 0 to VDS. At x equal to 0, the voltage will be 0, VDS should be 0. At x equal to L means what about V of X? VDS. Okay. Yeah, copy up to here. Write down. The current in the inversion region is given by I equal to QD into V. Yeah, copy here. Copy up to. Yeah, copied na? Yeah, next one. Now continuing this sequence here. Continuing here. So what is the integration of I into dx here? It is simply I into L. Okay. Now COX into W into mu n, because here electrons now, so that is mu n actually. Now what is the integration here? Integration of that expression VGS minus VTH. Yeah, this is simply VDS. I think minus VDS square by 2. I'm directly writing, right? So integration of this part is nothing but VGS minus VTH into some V. So substitute the limits now, then we will get VGS minus VTH into VDS. If you integrate this one, so if you integrate AX means what? X square by 2, right? So V of X by 2. So simply like this. Now what it is? Now I think this I can be represented as IDS, current in a channel, right? So here electrons are going from source to drain means what is the current direction here? Drain to source. So that's why it is IDS. IDS is equal to the final expression COX into W by L mu n into VGS minus VTH into VDS minus VDS square by 2. Right? Now what it is? This is the IV relationship in a MOSFET, or we can also say current equation of a MOSFET for N channel. Of a N channel, right? Yeah, copy. Yeah. So with this, IV relationship in a MOSFET is completed. Okay. We will continue next lecture. Thank you.